you. I'm going to also be spending a lot of time in the halo with my talk as well, but more in the stellar halo than the certain black medium. As I was introduced, my name is Nasser Mohammed. For those of you who haven't had a chance to meet me yet, I've been working with Ting and the DESI Milky Way survey working group at large for this project of studying stellar streams in DESI. I want to start this talk off by just a big question of what are we answering with our research here. And you guys can think about this for your research as well, just for a second. If you really get down into it, take away all the abstraction. What is the question you're getting at? And for one of us, that answer usually is the lambda CDM cosmological model. In some way, we're testing, either agreeing with or disagreeing with lambda CDM, where lambda is that energy density for dark energy, and CDM is the cold dark matter model. There's this really fun artwork from Claire Lemon, who's part of the cosmology team in DESI, showing that all these different observations are kind of holding and having some tension on the lambda part of lambda CDM, and there's this overarching feeling that something has to give in terms of either the physics is wrong or our understanding of one of these different phenomena are incorrect. And I want to propose very briefly something similar for the cold dark matter portion of lambda CDM as well. So we have the core cusp problem, which some people say has been solved, but that's still there. The missing satellites or just the lack of direct detection for dark matter properties so far. And I'm going to be trying to test or put some constraints on the dark matter models here using stellar streams. The important background is that the lambda CDM paradigm predicts that Milky Way-like galaxies have grown bottom up within some large dark matter halo that has the majority of the mass budget for that galaxy. The cold dark matter subhalo mass function, so the function of how many subhalos there would be at each mass, is scale-free, meaning that we have some halos the size, the Milky Ways are larger, 10 to 11, 10 to 12 supermasses. You can go all the way down to the Earth-sized mass dark matter halos out there that are predicted under this theory. And we want to try and probe this regime because different dark matter models predict different amounts of this dark substructure. And when you get down to the smaller masses, below 10 to 8, 10 to 7 solar masses, these halos can't form stars. They either can't retain a baryon or just don't let baryons cool to start star formation. So you get entirely dark substructure. That's very difficult to kind of sense that it's there because dark matter doesn't interact with baryons except for gravitationally, really. Stellar streams are also a prediction that we do see from this hierarchical model. We're saying that the baryonic portion of the galaxies grows, the disk and the bulge and the stellar halo grow from these infalling halos, dark dwarf galaxies with longer clusters. And as they influence from, they'll grow a leading and trailing tidal tail, and we see these as stellar streams before they eventually phase mix fully into the stellar halo. Stellar streams are very long, so and cool structures, so they're 10 to 100 kiloparsecs on order for the length. And because of this and the amount of the galaxies they span, they're likely to have collided with this predicted dark substructure that's out there. Large impacts, so 10 to 6 or larger dark subhalos mainly impact signatures directly out. You can see like gaps or spurs coming out like the infinite GD1 that we've been able to model with constraints on how massive those perturbations must have been. But those are spurious and infrequent and difficult to use to actually constrain the dark matter models at large. And what we can do instead, slide switch, is say I take one of these very cool thin stellar streams and I put it either on the left-hand side, cold dark matter, or right-hand side. You'd expect a different amount of perturbations, different frequency, different magnitude of these perturbations, so we can test based on the velocity dispersion, spatial dispersion, and all the substructure that we see. If you look at a population of stellar streams, what does it agree with more? Cold dark matter, warm dark matter, self-entrapping, fuzzy dark matter, lots of different stuff you can test with. For those of you who were here last week, Jake Niebauer showed his work looking at his semi-analytical way of simulating impacts, and you can turn up or down the amount of impacts from the CDM rate to above or below. or you can change the density of these subhalos, mass of these subhalos, all this stuff, and you get different distributions for how much velocity dispersion you'd expect for stellar streams broadly. And this is where we're going to bring in DESI. The DESI footprint for the Milky Way survey, which uses the bright time of the DESI survey, where the cosmologists can't see their little galaxies that well. And that overlaps with over 80 stellar streams. So by properly characterizing the stream using the DESI Milky Way survey, hopefully we put some constraints on the dark matter subhalo distribution. DESI is very useful for this. I'm working with the Year 3 DESI data, which has radial velocities and metallicities for over 15 million stars so far. This will be equivalent to about DESI DR2 when that comes public in 2027. And what we can do with that is get the line of sight velocity, which is very important. And we pair that with Gaia DR3 for the astrometry. So the planet sky motion, we can eventually get the full 60 motion for stars, characterize the full 60 kinematics of the stream using 3 velocities and 3 positions as well. So I'm going to walk through this cartoon of how we model the stellar streams. Our assumption for this modeling is that when we cut down and look at some field of stars, that the population of stars can be described by 2 distinct stellar populations, ones that are members of the stream, which I have as these O's, and ones that are the background stars, which are the dots here. It could be tough to kind of disentangle them in this physical space, this phi 1 and phi 2, which is already negatively rotated to be onto the stream. But if we plot one of the velocities, because these streams are infalling or foreign dynamically to the rest of the Milky Way halo, which is usually the stars below in the background, it has some trend that is distinct and stands out quite noticeably from the background stars. And you might say, Nasser, this is just a cartoon. There's no way it could possibly be this distinct to see these stellar streams. Well, I have proven you a fool. Here is the stellar stream. And you can see that this track here is the line of sight velocity trend as you go along the sky, or the silver stream, which is completely distinct from the background here as well. So it's a great starting point. Not all the streams look this good, but silver is my favorite example. We want to go in and say that there is some distribution of stars that are drawn for the velocity track here that is separate from the rest of the stars in the field. We then want to fit the scatter in that trend velocity, and that scatter is going to be what we compare to simulations like Jake's, where more interaction with small subhalos will increase the dispersion in the velocity. So overall, we can do this for any of the 4 parameters we're measuring, which is the metallicity, model of the metallicity, velocity of line of sight, and 2 proper motions. We say that for any position in phi 1 along the stream, there is some mean and some spread that we're drawing that stream property from that is distinct and different from the background at large. So we're doing a mixture of 2 Gaussian models. This is where Bayes theorem comes useful for us as well. The important parts of Bayes up here on the screen, we're saying that the probability of our model given the data in the posterior is proportional to the likelihood times our prior knowledge about the model. Now, I want to make clear that we are not doing a stream discovery tool, we're doing a stream measuring or stream characterization tool. So it's very useful that we take the known property that we know for some of these streams, the handful of stars that have been measured, and we put that into Bayes theorem to inform our model. So this is very useful to include that prior term. And we construct our likelihood as follows, where this first term here is going to be the stream likelihood. We have the fraction of stars total that belong to the stream versus the background. And so we have the likelihood that each star belongs to the stream, plus the likelihood that each star belongs to the background. And then we sample this with the MC affine invariant sampler and come away with some posterior values for what the best model parameters are to describe the data that we have, that we see in the field we cut down. So we're sampling 27 posterior dimensions total. And from that, we get our final parameters. We can then put those into our model parameters. We can put that into our likelihood function, and we can do the ratio of the probabilities in the stream and the total likelihood of a star between the 2 components, and that gives us a membership probability for each star. So what percent chance, based on our best fit model, does each star belong to the stream? And that gives us some nuance when assigning memberships for stream members. We're going to apply this in this talk to the C19 metal poor C19 stellar stream, which is an extraordinarily metal poor globular cluster population. And if we understand, it's below what we thought was the metallicity floor for globular clusters for a while. This is distribution of metallicity of intact globular clusters looking at the Phoenix stream, and C19 breaks that even further. And C19 is just a peculiar test subject in a few ways. The other one I'm going to mention is the fact that its velocity dispersion, that measurement that we're going to use to compare simulations, is a lot hotter than what we'd expect for a non-dark matter dominated progenitor, then disrupting and becoming a stellar stream. So there's been a test that we're saying this might challenge the CDM part of lambda CDM. So we're going to be throwing our mixture model at this here. The most recent measurements have 22 spectroscopically confirmed, so using radial velocities, members of C19, and it spans over 100 degrees in the sky too. Unfortunately, the DESI Milky Way survey only has a footprint for about 45 degrees here. So we're working with a limited sample, but all in all, we still walk away with 42 high probable members for the C19 stream. So that's, if we include, there are 6 of those 22 stars that are in DESI, and we recover all those 6, and we have 36 new members on top of that, where we're saying a member is anything with above 80% membership probability. So that's over a 250% increase in stream members. And if these stars, the top of the figure, are the known ones from the U1 et al. Work, and we're getting all these dimmer stars after that because we're having radial velocities for magnitudes dimmer than what is available for like the RBS catalog in Gaia. What we can do with these is to measure the properties that we're interested in the stellar stream. So from this middle panel, which is the velocity along the stream, you measure that there is a 8 kilometers per second scatter about, which is once again way hotter than what we expect for most globular cluster destructive scenarios, which is around 2 to 3 kilometers per second. And we reaffirm that this is a very metal poor stellar population with our demonstration of spread metallicity also consistent with literature. What we can do is compare this directly to some simulations. So Ray Carlberg, who's a Ryan's professor here as well, has some simulations where pretty simply we have some fixed mass bulge and a growing disk potential, and we throw a C19 progenitor into this with different subhalo types, and we compare with our observations from these simulations. So I'm going to play this animation here. We're going to see the C19 progenitor thrown in, it's fluttering around, disrupting, and all these flashes are different interaction, either from the empty dark matter halos of those hollow ones, or the few baryonic halos that we have in it, which are like dwarf galaxies and no globular clusters. And if we remove all the dark matter in the simulations, we end up with a dispersion for C19 of around 2 kilometers per second, which is not consistent with our observations. But when we throw it into the simulation of all these dark matter halos, you can just see visually we're getting a lot of substructure, these breaks, these kinks, and all that stuff, which we want to compare to our observations. So Ray's going to put this on as preliminary, so I put it in big text here. This is showing for however long we allow that C19-like progenitor to exist in the simulation. What is the width of the velocity that we see, velocity dispersion in the stream? So this green band is C19 from the observations, and this is for CDM and 2 different types of moving dark matter. And the overall conclusion is that the best agreement here is with CDM, but there's a lot of scatter, and it's also consistent with moving dark matter. So what we really need is to use for a lot more streams to get any constraining power. And that's just going to be the first part of my thesis as well. It's characterizing as many of these streams as we can in DESI. So I will leave up, actually I'll talk about it. I think I have time real quick. C19 takeaway is an extremely metal poor population. And I think I take issue with the naming of the stream as well. I don't see 19 stars, I see more like 42 stars total. So new name proposed is 3. And mixture modeling for studying streams. And we really just want to compare to simulations for as many streams as we can to get good, robust constraints on these stellar streams. I'll take questions. Thank you. Yes, Josh.
All right, I gotta be that guy, or like that statistician.
Yeah.
So you showed some results from your MCMC run with a lot of parameters. Did you do any checks to make sure that like things had converged or that like you're well behaved, effective sample sizes or other relations?
Yeah, we chains all up to converge. I have extra slides with our posterior predictive checks here. So this is where we take our models that we fit, we sample from them with observed errors and we compare with data. So it still doesn't show up in the dark mode, so I apologize for doing that for the talk. But generally, the distributions agree. We do it just for the stream model as well. And we can look just if we plot the quantile, if it's directly along this line, saying that we have good agreement. We are having issues with the skew of the proper motion distributions, but we actually are unable to constrain the dispersion of the proper motions, and so we have to fix that. So that might be what's arising here, but overall, I think our post-predictive checks are saying the models work all right, and there are no correlations like with the quantum plots as well that are very concerned.
Does it great?
Yeah.
Maybe slightly related, you had your probability larger than a half, which is not that great, but
Yeah.
is it basically that does it matter if you chain only your stars with probability greater than 0.8, you still get the same sigma? Because
So yeah, I didn't include it in my extra slides, but if we plot a histogram of the membership probability, we basically have a bunch of stars with nothing, like 3 stars between 20% to 70%, and then most are above 90%.
okay, so
It's just these ones with really large errors that are getting low membership probability for the faintest stars here as well. But I think we have 37 stars above 95% membership probability, and we just included ones with larger errors.
you basically just looked at, okay, well, look, there's a clear distinction between the two levels.
Exactly, yeah, it was my discretion.
Yeah, that's fine.
Yeah. Yes.
So what's the sort of paradox of the orbit? Is it coming through the disk of the galaxy?
And so C19 is, and this is something I should have touched on, is it's at apoCenter right now, which is 20 kiloparsecs galactocentric. Its pericenter is 10 kiloparsecs. It's in a very polar orbit though, and so
How is rate modeling with this?
it is, here I have it in my speaker notes, it is a Miyamoto Nagi disk growing.
And there's been are there GMCs and so forth in it?
These, I don't think he has GMCs, but known dwarf galaxies and globular clusters are.
I'm just worried about when they goes to the disk and enhance the dispersion, whether it creates models.
That's a good question, and I'll also point preliminary for missing. But yeah, thank you, good question. Chris.
I think you said the disk is growing, but is it growing in that way we're growing a better CBM with full simulation, logical simulation, or is it growing in a prescribed fashion?
I don't know. Yeah, we're writing that up and it'll be included in the discussion for that, but yeah.
I wonder how much that early history affects the current stream.
That's a good question, and something I'll note as well is that if you compare with Jake's simulations that he's running, which are the I believe they're static we'll call it hosts, but he can't get what we see with his CDM simulations, but with regular agreeable CDM. So there's, I guess, tension between the different simulation models. But my work is the observed stream.
Tiny detail, why do you start at 7 giga-years?
It starts sooner, but like it's thrown in at 0 gigayears. It's how
Okay.
It's just we're plotting after 7, but it starts to get close to observed dispersion.
I see.
Overall, yeah.
What's I don't know, what's your like error budget like in terms of these constraints or the constraints from the data? Like if you had better
line of sight velocity, so you have better power motion, so you have better just. But what does that do for your ability to stay like? CDM stands for versus.
I think that's a good question. The errors we're having on the velocity dispersions are plus or minus a problem per second for the mean. So those are large, but the idea is hopefully for a lot of streams, we can kind of constrain that away on a population level. The smaller uncertainties on the mean velocity dispersion, I would kind of just shrink this if we're comparing with raised bands. And then there's finer. One thing that there's generous here is how long the stream lasts in the halo. So a longer time in the halo can get you those large dispersions than shorter times with more subhalos. So that's one thing I want to work with. It'll just give us.
And do the streams still look like each other if you only use the sigma now? But presumably you have, like, I don't know, the length of the stream and how much it is still a stream rather than just two clumps.
It also compares the phi to dispersion, so the dispersion property. And there is and we do KS tests for the distributions to see that it makes sense that the observed distribution of phi 2 agrees with the simulated one, and just let it run out. You see substructure and gaps very similar to what we observed. With a kind of dirt sphere and substructure, the spur coming up here. So visually it's in agreement, but also those simulations, we are working to put a selection function on just solar mass particles, but we want to be able to do the same isochrone cuts that we do and see what we observe.
I guess a bit like this question. I think partly it was asking other things that you can't measure now, but better proper motions, would that really help you?
Better proper motions would be amazing, and then we could also do. Right now, we're just on a fixed. I don't even show them fixed dispersion and proper motion, but if we have better errors at from us, it's 18 kiloparsecs rather than like almost 10 kilometers per second error. We can get transverse velocity dispersion instead of just line of sight, and that would be better. But that's what we're hoping for, like a Euclid and Rubin measurements down the line for the high precision astrometry, or Kevin's work using Hubble observations in conjunction with Gaia and stuff to get really small errors in population.
On targets that you pre-selected, so it's not so.
Oh, well, hopefully we cross match it with that and just do the same.
Yeah, I know. You find which one to look at the tunnel, right?
Oh, yeah.
This is 100 degrees. You can't do all of
We
it.
can't do that.
Yeah. Beautiful.
Okay, awesome. Thank you, speakers.